All right, so generally we're going to have a lot better presentations of this, but turns out that Chapter 1, Section 2, I never really made a PowerPoint for. So here we are with PreCalculus at our 1.2 notes. In Chapter 1, we're kind of skipping around and just doing the parts that are helpful to us. So 1.2 notes is what we're doing today, and it's called Functions and Their Properties. If you go online to the textbook that we have, the textbook online is your 8th edition, and the textbook that we actually physically have or have been going off of up until now is the 7th edition. So far, they match up. So it doesn't matter if you use the online one or if you have a physical copy somehow. If you would like a physical copy of the textbook, you should totally email me, and you can pick it up on an SEL day if you would like. All right. So here we are with our notes, just me writing today. All right. So we've got functions. Okay, so if you don't remember that word, functions are going to be functions if they pass the vertical line test. All right, and again, VLT is your vertical line test. So the idea is that whatever graph that you happen to have, if you draw the graph and make any vertical line anywhere on the graph, if you only touch the actual graph itself once, it ends up passing the vertical line test because it only touched it once. If you end up having an equation, which would then not be a function, so an equation that, for instance, has some sort of this going on, okay, which is actually the inverse of the first one here. But the idea is that if you draw any vertical lines there, oh my gosh, the problem is that one vertical line will touch it more than once, which is what we do not want. So this one does not pass. And so because this one passes over here on the left, it is a function. And over here, it is not a function. And again, the reason that you would need it to be a function versus not a function comes into play when we later on talk about inverses and all of these good things. So that is your vertical line test. When we talk about functions and this vertical line test, the whole idea is that each of the equations has one input for every one output. So for instance, if I go ahead and plug in the number 5, I'm only going to get to one spot on this line, versus over here, if I plug in number 5, I'm going to either get this number up here or this number down here. So the idea is that if you have a function, every input, meaning your x's, has only one output, meaning your y value. All right. So the next thing that we are going to talk about is domain and range. And so kind of mentioned in this part here when we talked about x's and y's, your domain are your x values. And so when we're talking about the domain of a graph, let's say that the graph for some reason is this one here. All right, it turns out that this graph is going to go on forever in the direction here all the way to negative infinity. It's also going to go on forever, yes, in this right direction forever. And so, whoops, in that case, our domain is going to be from negative infinity to infinity. But the way that we write that with our mathematics is that the domain goes from negative infinity, and we're talking about our x's, and we're talking about that's the lesser amount, and that it goes to infinity. So this is the way that we are going to write it, and as much as you love the fact that this is an option, it is not anymore. One thing about this is that the book starts doing point notation, which is just not my cup of tea. But if you ever look at one of the answer keys, for instance, the book answer key to what is the domain of this function over here is actually going to look like this. So it's going to look like a coordinate, okay? And so the book answer has coordinate notation, and what the idea is that if you have a bracket here, a parenthesis versus a bracket, you have less than symbols. So I would change this if this was equal to, which it never could be equal to infinity, but if that's equal to, then this parenthesis over here actually becomes a bracket. So the idea is, in this notation, that if you have any less than or equal to's or greater than or equal to's, you're talking about brackets. But if you have any less thans or greater thans, you're always talking about parentheses. So again, that's just the idea that the book has. And if you don't understand that, that's okay. I do not teach that notation necessarily, but it will be used at some point in your text. So the other piece, other than domain, is your range. And so again, if we go back to the possible, in this case, y values, you're talking about how far up and how far down does it go. So looking at that image that we had earlier, this one definitely goes up until infinity, all right? So it's going to go all the way up until infinity. But then it only goes down until whatever this vertex point is. So let's say it's -5. All right, and so in that case, we're going to say that our range is from -5 to infinity. And it looks like it's going to include -5, because it's right there on that dot. So the notation is actually that the range is -5 included, so notice the underlined part. And we're talking about y values, and then infinity, which we never include. It can never be equal to infinity because there is no end to infinity, so you can't equal it. All right, and again, if this was the textbook answer would end up having a bracket because we're talking about equal to, so -5, and then it would have an infinity with a parenthesis. So it looks very weird, especially when the endpoint might be a point as well, and so you think that you're graphing something, but you're not. So that's at least the start of that. All right, the next thing that we're going to talk about is continuity. Continuity. All right, so if something is continuous or continuous, all right, that would mean that it goes on forever. But there are things like removable discontinuity. So as we look at different types of functions or equations, we are going to see something like, there's a graph. All right, so we see a graph that kind of goes on, but then, oh my gosh, at this point right here, there's this hole in the graph. And yes, that does actually happen, and that one is called removable discontinuity. And so what you're going to be presented with is the fact that something, this image is given to you, and you're going to have to say, is it continuous or not? And you would say, this one's not continuous. And then they would say, what kind of discontinuity does it have? And you would say, removable. All right. We also have something called jump discontinuity. So if you can imagine what that might be. Jump discontinuity is going to be some sort of graph that all of a sudden stops and then jumps up to be something else. All right, and it does happen at that one point, and so it is still continuous because it goes without stopping necessarily. But again, we're going to call this jump discontinuity. All right, we also have something called asymptote discontinuity. So I'm going to put that on the next page here. And asymptote discontinuity is kind of like when we were doing exponential equations, things like that, and your graph ends up kind of having this, well, asymptote in it. And so if you have asymptotal discontinuity, it could be asymptote discontinuity that's up here across, or it could in fact be down depending on if the equation goes on forever or not. So either one of those could be asymptotes that happen with this equation that like approaches it but never actually touches it. So either way, that's asymptote discontinuity. It exists as well. All right, the next thing that you're going to be asked about is something called boundedness. And boundedness just means that there are these horizontal lines that represent the maximum or minimum. So we're looking for the horizontal kind of asymptotes. That bound or surround the function or equation. So if we think of a very famous, or one that we will in fact be looking at a lot, equation, we could, for instance, do a sine or a cosine wave. And so what happens with this wave is that it doesn't actually ever go past, in actuality, of 1. But the idea is that there's this peak that it only goes to, and in fact this peak at the bottom as well. So this is your bound. This is what we call our upper bound, and this would be the lower bound. And so there are 3 answers for this. Is it bounded? And you would say, yes, it's bounded above, or you would say it's bounded below, or it's just bounded, which means both. So you could have bounded above, and you could even say at y equals 1, or whatever it happens to be. Then you could also say it's bounded below at y equals -1. Bad moment here. Or you can just say bounded in general because it's got both, above and below. So that is your bounded. All right, so continuing on, after boundedness, you may be asked if a function has some extrema, and yes, that is the word. It just means extreme points, meaning very high points or very low points. So you are going to be able to say if it has a local minimum or a maximum. But again, absolute would mean the absolute minimum or maximum. So either way, if you look at an image of some sort of polynomial. This right here would be your extrema. And so would this, and so would this. Okay, so those are all extremas. But when you're looking for a local maximum, for instance, this one is your local maximum versus over here would be your local minimum. All right, but then if you're actually looking for an extrema, the most extreme point would be right here because it is your maximum point. All right, so if you're looking for a maximum or a minimum, that's your extremas. And they want you to give it as a coordinate. So whatever it is that you are given, if this is a coordinate point of, say, 5, 6, you would want to say, yes, there is extrema, and it's at 0.56, or whatever it happens to be. All right. The next idea that you'll be asked about is symmetry. And so you're going to look at a function and say, is this symmetric or not? And there are a few ways that something can be symmetric. They can be symmetric across an axis. And so you would want to make sure that you are saying it's across the x or the y axis, the up or down or the left or right axis there. And other than being symmetric across an axis, and you would want to say which one, it could be across a line of some sort. So it could be a horizontal line. And the way that you would say a horizontal line is y equals whatever number that is. If it's a vertical line, other than the axis itself, that's going to be an x equals a number. And then you can actually have a symmetric about the origin. So that means that whatever it happens to be, for instance, this image up here, the equation of x cubed is symmetric about the origin, because this point right here at the origin would be kind of that spinning piece. So if you put your finger on that spinner and then spun, it would in fact go around the origin. Other than about the origin, it could be about a point as well. So we could end up spinning it around a point other than right here. For instance, it could be up here, and you'd have the you'd have the graph kind of going through a different point. So that's your symmetry. So it's asking, is it symmetric or not? And then when it is symmetric, identify, is that across an axis of some sort or a line, whatever it happens to be. Then they're going to talk about end behavior. Of an equation. All right, and so from end behavior, you are going to be saying, and maybe you remember this terminology in Algebra 2, but basically you're asking as it goes to the right, you're going to use this notation that says the limit as x goes to infinity, you're going to say that the function goes to something. So maybe a number, maybe infinity. If we're talking about it going to the left on the image, that would be the limit as x goes to negative infinity of a function. And so if we look at this graph that we were just talking about with y equals x cubed, so if we're looking at this x cubed graph, the idea is that it goes to the right. As it goes to the right, it goes to infinity, right? And as it goes to the left, it goes to negative infinity. It's going down. So if I was going to fill that in up here, we'd have an infinity and a negative infinity. So you're looking for end behavior. Sometimes the graph could end up kind of having an asymptote, and so then you'd maybe say that it approaches the number 10 or whatever it happens to be that it approaches. So you would have changed this to a 10. No, sorry, this one to a 10. All right. So the next thing that we are going to talk about after I go back to there, is even and odd functions. So the next piece is an even function versus an odd function. And so an even function usually has symmetry, that's line symmetry. So has vertical line symmetry. So for instance, the most widely known one would be a parabola. So as we're looking at a quadratic or a parabola, definitely have this vertical line symmetry, and so that one would be even. Another idea about even is if it has even powers, or the highest power is even, then an even number, then you're going to be okay as saying an even function. But again, you're just looking for something that has a line symmetry, a vertical line symmetry. The other part is an odd function, and odd functions usually have rotational symmetry. And then we could also have an odd power as well. So, for instance, x cubed would have a rotational symmetry and it's an odd power. So the idea of your assignment is that we are going to be looking at a bunch of functions and they're going to ask you each of these questions. So you're going to look at it, maybe graph it, or they'll have an image of it for you. And you are going to look at it and talk about, for instance, its end behavior, or if it's symmetric or not, or what its extrema are. So you do have an assignment that you will have time to work on tomorrow, but this is the notes for today, so hopefully you got some of that down.